طيب السلام عليكم. So today let's continue with chapter 5, and after that we will discuss chapter 6, which is the stability of linear feedback control system. And I will finish chapter 5 with two, let's say, problem. The first one, let's assume we have the following block diagram. So here, let's assume we have example. And for the following block diagram, and let's plot it here. Alpha over S plus 1, and let's assume here we have a feedback with, again, let's say beta, and let's assume this one is a positive one. Also here we have integrator 1 over S, and this is my output Y of S, and here I'm having the feedback configuration. This is R of S, and let's define this one to be E of S. Now here for this simple, let's say, block diagram, I need you to, okay, let's roll out a lot of questions. The first one, the type number.
One.
Why one?
Because we only have one integrator.
Yeah, we have only one integrator in the loop again, and this integrator is not cancelled by any other factor, correct? If I here, for example, if I'm having here S, this S will eat this S, so simply I will end up with, let's say, 0 type number. But simply here, for this case, I'm having what? I'm having type number equal to 1. Thank you. Raha, correct?
Yes, doctor.
Thank you. Okay. So the type number is equal to 1. Now, who can give me KP equal to what? KV equal to what? KE equal to what? KP, KV, KA. Now, position error constant, velocity error constant, and acceleration error constant. Do you remember the definition of the KB was what? It was the limit when S go to 0 of the loop transfer function, correct? We call it GCG. So here the loop transfer function is actually what? I need to simplify this one, correct? Yeah? And who can help me with this one? Who can help me with this one? It will be G over 1 minus G beta, correct? So it will be alpha over S plus 1 minus alpha beta, correct? Yeah? Yeah, this is the configuration. If replot it here, and here let's assume this one is G, and here I'm having H, and here I'm assuming a positive feedback. So this is the R here, let's assume this is the Y. So this is a positive feedback, so G over 1 minus GH, correct? Yeah. If this one was minus, if this one was a minus here, then this will be plus. The same thing here. If I put here minus, this will be what? Plus. Understood? Yeah.
Yes.
So now this one, let's say GC can represent certain transfer function. So I will multiply this one with that one. So simply here I will get the limit when s go to 0 of alpha over s plus 1 minus alpha beta multiplied by 1 over s. By the way, I don't need to calculate this one. Do you know why? Because this type number is what? Raha, the type number is what? 1. So if the type number is 1, then E steady state due to unit step equal to what?
Minus 1 over beta.
Type number equal to what?
1.
And if the type number equal to what, then the error due to the step input equal to what?
0.
0. Yeah. Why? Because KB equal to what?
Infinity.
Yeah. So simply this one I don't need to calculate actually. But simply here because I need to find the loop gain. KV equal to what now? If I need to calculate KV.
0.
No. This type 1, Raha. So KV is the limit when S go to 0 of S GCG. So simply this means that one of the S's here will eat this one. So it will be alpha over S plus 1 minus alpha beta evaluated at S equal to 0. And this will equal to what? Alpha over 1 minus alpha beta, correct? Yeah. Yes, but Ka equal to what? K equal to what?
Limit لل squared
So
بالg.
it's the limit. If I need to evaluate S go to 0, S square, GCG. But I know this type 1, so this will equal to 0 for sure. Do you remember type 1? In type 1 system, when we plotted a table like this one, and we say there here n, and here we have the 0, the 1, the 2, the 3, the type number, here the input, which was the step, let's say A over S, the ramp A over S square, and here we have the parabolic or the acceleration input A over S cube. When type 1, this was the steady state equal to 0 because KB equal to infinity. Here it has a value, KV has a value, but here KA is equal to 0 and E steady state will equal to infinity. So this one also I don't need to calculate, but if you evaluate the math, it will give you 0, correct? Should I evaluate it for you? It will equal S square alpha over S plus 1 minus alpha beta. Now, according to the Pacman theory, this will eat that one. And I'm evaluating at S equal to what? 0. So simply, this is what's multiplication. So this will equal to 0, correct? Yeah. Yes?
Yes, doctor.
Okay, so now who can give me the steady state due to unit ramp? Yeah. Now, under the assumption the system is stable. Because you know that if the system is unstable, there is no meaning actually for the type number, and there's no error signal. The error signal will go to infinity. The system is stable. Or if I need to let's say neglect this one, I will make the magic, and here I will put negative. Here it will be plus. Yeah. And here this will be plus, and this will be plus, and this will be plus. And nothing is changing, except that now I'm assuming that alpha comma beta is greater than 0, and this is sufficient for me for the stability. Later on we'll discuss that. Yep. So now who can give me that EC state due to unit ramp is equal to what?
A over KV.
So
One
this will
alpha
equal
beta
1 over KV, which is
1 plus alpha beta على alpha.
Right. Yeah. Do you see, this is very, very simple. Yeah. This is very simple. Now, who can design alpha and beta such that, let's say, TS is equal 4 seconds, and let's say the percent overshoot is equal 4.32%. So simply from those information, what I can get from this information, TS is equal 4 seconds. What I can get from here, we know that TS is equal to what? 4 the time constant, or 4 over sigma, which is 4 over zeta omega n. So from here we can reach to a conclusion that sigma is equal to what? If TS equal to 4, then tau equal to what?
1.
So sigma is equal to 1. Thank you. And from the percent overshoot here, what I can get? We know that the percent overshoot is equal exponential of minus zeta pi over 1 minus zeta square, correct? So from here I can get what? I can get zeta. I can get zeta. Now if I do the math, you don't need to be a genius to do that. Zeta will equal 1 over square root of 2. And simply if you see this number, if the percent overshoot is equal 4.32%, then know that zeta is equal 1 over square root of 2, which is actually 0.707. Now, if I know zeta and I know sigma, can I know the characteristic equation, the desired, let's say, characteristic equation? This is actually called the desired characteristic equation. Why desired? Because this one has desired transient response, settling time, let's say percent overshoot. So from the knowledge of zeta and omega n, we can here write the desired characteristic equation. Which is equal S square plus 2 zeta omega n S plus omega n square. And we have S square here. And zeta omega n, we have it, 1, correct? So this will be 2S, yeah? Yes? And simply here, we have this one, zeta. So from here, we can calculate what? If I know zeta and I know sigma,
Yeah.
I know that sigma is equal zeta omega n. So from here, if I need to calculate omega n, this will be sigma over zeta. And this will be square root of 2 actually, yeah? Yes, 1 over square root of 2 is square root of 2. So here, what I should put here? Omega n what?
2.
Omega square, thank you, 2 equals 2. So now, what I'm having here, we have here something we call it the desired characteristic equation, which means that in the end of the day, I need my closed loop system to behave in certain manner similar to this characteristic equation, or let's say the response of the closed loop system, I need it to be characterized by this given or the desired characteristic equation. So this can be seen as my reference model. I need my closed loop system to be identical to this characteristic equation. Why? Because this characteristic equation set a certain requirement on the settling time and the percent overshoot, which I need. Why I need? Because due to the application, due to the certain requirement, I need my response to have, let's say, or I need my response to have a settling time equal to 4 seconds and the percent overshoot equal 4.32%. So what I need now to find alpha and beta, I need to find alpha and beta. How I can do that? Muhammad Mahmoud. No. Muhammad Majdi. Muhammad. Yeah. Can you help me with that? I need to find alpha and beta. Now, this is what? The desired characteristic equation. So I need to find a characteristic equation from the block diagram. So where is the block diagram? This is the block diagram. And I think I changed the sign here, so this will be plus. So now, can you give me the closed loop transfer function for this block diagram, Muhammad? Yeah. Give it. Alpha, okay.
على S plus 1. Beta.
Alpha over S plus 1 زائد alpha beta. Okay.
على لا.
Okay, let's do it one by one. Over S over 1 plus this one, correct?
Yeah.
I think this is what you need to tell me. Now, can you simplify this one?
مش من واحد رقمات
Yeah. But simply, I'm too old to do that. So you will multiply by this one, correct? Up and here. If you do so, you will end up here with alpha. And here you will end up with what? S square plus 1 plus alpha beta. S plus alpha, I think. Yeah?
Yes.
Thank you. Do you see how easy is that? Yeah, it's very easy. So now, here, for this transfer function, where is the characteristic equation? You know, this rational function, which is n of s over d of s. And we know that d of s is equal to 0 is my characteristic equation. So where's my, here, the block diagram characteristic equation?
المفروض اللي هي هذا الكوفيشنتس ولا
This is the characteristic equation. S square plus 1 plus alpha beta s plus alpha. Can you memorize it for a second? I need to write it down.
Yeah. Sure.
Okay, thank you. Give it to me now. So from the block diagram, just a minute.
Square.
S square plus
1 plus alpha beta.
Okay.
S plus alpha.
Okay, so can you now give me alpha equal to what?
Okay, 2.
Yes, thank you. Can you give me now beta equal to what?
هاي 2 المفروض تكون -1.
So simply you are telling me that I need to compare, huh? Yeah, this is what you are doing. So simply here I'm having two unknowns. I need two equations and I'm having the two equations, which are the coefficient of s to the power 0 and the coefficient of the s to the power 1. So simply here you are telling me that alpha is equal to 2, and this is correct.
Beta is loss.
Yeah. So 1 plus alpha, you need to do the math, huh?
Yeah.
And from here, according to Muhammad, alpha is equal to
1 over 2.
I will not calculate.
دكتور
Over Muhammad. Yeah.
دكتور في ممكن اتوقع نحسب الفا من الستيد ستيت اليونت رامب اللي فوق.
We can do that, of course. But simply, okay, east state is equal to 0. Yeah. So
Yes.
how you can calculate?
لا لا
آه.
من الثاني من اليونت رامب اللي هي 1 على كي في كانت 1 بلس الفا بيتا على الفا، فالفا اكيد
Yeah,
كونستنت فاكيد هي
but simply I'm not giving you any value for this east state. I know you mean that you can calculate it here from a second equation, you mean, huh?
Yes.
Yeah, but simply it will be the same, huh? Why? Because you know that I need two equations to solve two unknown, and those equations must be independent. Yeah.
Yes.
Yeah. So simply, if I'm giving you a value for the east state due to ramp, yes, you can use it, of course. But simply here, if I find the characteristic equation, then it's a piece of cake, cheesecake actually. Yeah. What I need to do is to compare the coefficient of the same power of s, correct? So this actually from s to the power what? 0, I'm getting alpha is equal to 2, and from the coefficient of s to the power 1, what I'm getting 1 plus alpha beta is equal to 2. Plug and play, and you will get alpha according to Muhammad. Huh? I'm not sure about that. Okay. Now, what else here I can?
لا دكتور بس سؤال، البيتا بنص مش الفا.
This is my mistake. This is my mistake. Yeah. Actually, here I'm plugging alpha, so I will find beta. Otherwise, I will get 1 over 2 equal to 2, and this I will get Nobel for that. Okay. Yeah. This will destroy all the sense, man. Okay. Now, can I design alpha and beta such that the response is critically damped? Alpha and beta equal to what? If I need my step response to be critically damped.
zeta equal to 1.
Zeta equal to 1, okay. And the roots are what?
Same. Repeated.
Repeated, yeah. Negative, real, and repeated. So I need now S plus omega and square is my characteristic equation, correct? Yeah. So this will equal to what?
Yes.
S square plus 2 omega and S plus omega and square, or simply from here put zeta equal to 1. Yeah. Now, in this case, I will have here S square, and here I'm having 1 plus alpha beta S, and here I'm having alpha equal to 0. Yeah. So from here, I will get alpha is equal square root of omega n. Yeah. Correct. And from there, I can get 1 plus alpha beta is equal to omega n. Good.
Alpha equal omega n squared.
Yeah, you are right. Alpha is equal omega n square. Yeah, thank you. If I compare this one. So simply here, now if I need to find the value accurately, I need to specify another, let's say, another requirement such as settling time. So if I say that the settling time Ts is equal, let's say 4 seconds for simplicity, this will give me what? Sigma is equal to 1, which means that omega n is equal to 1. Why? Because zeta is equal to 1, and I will end up with what? Alpha is equal to 1, and beta equal to what it will be? Beta will equal 2 minus 1 over 1, correct? Which will equal to 1. Yeah. Okay. So here the root actually is what? S equal minus 1 will be. Yeah. This characteristic equation is S squared plus 2S plus 1 equal to 0. Good. Yes. Now,
Yes.
let's discuss another example before going to the next chapter. And for that, I will choose the following example. Let's assume that I'm giving you a response, a unit, or a, let's say a unit step response. And this response has the following, let's say, or this system has the following response, such that this value is equal to 7, and the input is, or the desired is 6. Good. And I'm giving you only this information that the settling time is equal 4 seconds. Why I'm choosing all the time 4 seconds? Because simply this will give me a 1. Huh? I'm too old to calculate it. TS is equal 4 seconds. Now, here the input is not unit step, the input is 6 actually. Yeah? Why? Because the desired. Yeah? And this is the input. And this actually is the step responses. Yeah. Now, can anyone answer what's the type number of this system? Can anyone tell me what the type number of the system? And for that, let's choose Walid.
نعم دكتور.
Can you tell me the type number of the system is what?
مش عارف صراحة دكتور. ما كان عندي امتحان وما حضرت.
متى ما حضرت؟
الأحد.
Okay, let's think about it. If the system has error due to step input, then the type number is 0. Good. This system has steady state error, or the steady state error is equal to 0 for the system.
لا في steady state error.
So can you tell me the steady state error due to step input is equal to what here?
1.
Huh? The steady state error is what? You will tell me it's R steady state minus Y steady state, correct? R steady state is what?
6.
Yeah, thank you. Y steady state is what?
7.
Steady state value, huh? The final value. This system still where?
6.
So 6. So 6 minus 6 equal to what?
0.
So the type number is what?
1.
At least 1. Correct? Because maybe it will be 2. Yes? But it cannot be 3. Why? Because this system is second order system, yeah? So at least what? Type 1. Yes?
Yes.
Good. Now, who can tell me the closed loop transfer function? The closed loop transfer function.
One, doctor.
Closed loop transfer function equal to 1. This means that the relation is static, or identical, which means that y r is equal to y. And this
Yes.
is impossible in physics, man. Transfer function. I need to find y over r, which is the n of s over d of s. Yeah.
Yes.
sigma equal to 1.
دكتور احنا مش سامعين اذا في صوت.
ما في صوت دكتور.
فصل النت عنده شكله.
Okay. I think I lost connection. Yeah. Now we are back here. Just a minute to continue with this one. Okay. Okay, cancel. It will be the same. Okay. Now we are returning back. Okay. So I need to find the closed loop transfer function, which actually I need to find the n of s and the d of s. Yeah. So who can tell me how to find the d of s?
sigma equal to 1.
Okay, from here we know that t of s is equal for the time constant, which will equal 4 over sigma. So from here, sigma, which equal zeta omega n, is equal to 1. Thank you. From this information. Then
zeta equal to 1, I think.
zeta equal to 1, I think no. Why? This one has overshoot. This one has oscillation, yes or no?
No.
Okay. How? This oscillation, do you see it? See. It will oscillate, yeah? Yeah. Do you know the meaning of the oscillation? That I'm crossing something and return back, yeah?
Yes.
So I'm crossing here, yeah? I'm crossing this line, then I'm returning back. So this system has oscillation. If this system has oscillation, then for sure zeta will be less than 1, correct?
Yes.
So this case is actually what?
1 over zeta.
Yeah, the under damped, yeah? Correct? This is the under damped case, yeah? So from the percent overshoot, can I find any information, or who can calculate the percent overshoot for me? Do you remember the percent overshoot equal to what? It was y at TP minus y steady state over y steady state multiplied by 100%. So this is equal to what? Y, the maximum point here equal to what?
7.
And the steady state equal to what? Yeah, so it will be equal 1 over 6, yeah? Or this equal 14%, yeah? 14%. Now, we know that the percent overshoot is equal multiplied by 100% is equal to exponential minus zeta pi over 1 minus zeta square multiplied by 100%. So simply from here, I can get a relation between the percent overshoot, yeah, to find zeta, which means that 14 or 0.14 is equal exponential minus zeta pi over square root 1 minus zeta square. So can you solve this equation to find zeta? I will take here the len and I will take here the len, correct? Taking the len, what I will get?
بس دكتور 1 over 6 هي 16.6.
16.6, okay. So let's change this one to 16.6%. So here the same, it will be 16.6. So now I will take the len. If I'm taking the len, this will equal to what? Should I calculate or you will calculate for me? So here I'm having the len.
1.79 مع سالب.
Yeah, in the negative. So it will be minus 1.7. I think I have 9.5 something, huh? So if I need to accumulate, it will be 1.18, correct? Yes. If I need to stop in the second digit, yeah, I cannot make it like that because it is 7, 9, 5, 6, correct? I think 7 here. So if I need to stop in the second digit, I will say the 7, this will be 6, and this will be what? 1, so it will be minus 1.8. Huh? This is the logic thing that if you need to do approximation, something we learn from the third grade, I think. Okay, then I will have here what? Minus zeta pi over square root of 1 minus zeta square. Can you help me to solve this equation? To find zeta? Huh? Now this one, someone will say it will be 1.8 square equal to zeta square pi square over 1 minus zeta square. Yeah. And simply in the end of the day, I will get what? I will get okay, zeta square pi square. Let's make it more clear. So this will equal zeta square pi square plus 1.8 squared zeta squared is equal to 1. Yeah, so simply zeta will equal to 1 over pi square plus 1.8 square under the square root. And this will give me what? Can you calculate for me?
0.49.
0.49?
0.497.
So 0.5. Yeah. Either you are putting 0.97 here, but because here I'm stopped at the second digit, huh? So I need to do the same. So the 7 will be approximated to 1 here, and the 9 will be approximated to 1 here. So this will be 0.5, correct?
دكتور بس طلع معي
دكتور
0.276
0.276
لانه
بيطلع.
في روت مش واخدين الروت هون و 0.276.
It's according to, okay, I will take your answer. Actually, I don't have the answer, so you are calculating. You are my calculator man. So the answer is what? 0. What?
0.276.
0.276. The same thing. This will equal 0.3. 0.28. Sorry. Yeah. Correct. Yeah. If I need to approximate, if I need to stop in the second digit. Yep. So now I'm having zeta and I'm having what? Sigma. So I can find what? Omega n, correct? Yeah, from here. Yeah, here. So from here, what I can calculate? Omega n equal to what?
Equal to zeta 0.28 sigma 1.
One over sigma, correct? Omega n is equal 1 here, so omega n equal 1 over zeta. 1 over zeta. So now I'm having zeta here, so from here I can calculate omega n, which will equal 1 over 0.28. Can you calculate that for me?
3.57.
3.57.
3.57. This one is rod per second according to the SI unit. Okay. So now the characteristic equation will read as what? It will read as S square plus 2 zeta omega n S plus omega n square. If I plug and play, this will read as S square plus, I think it's 2 here, S because sigma was 1, and omega n square. Can you square this one for me? 3.57 squared equal to what? 10 something?
12.7.
Yeah, so it will be 12.75, I think. 449. It will be 5, huh? Yes. So good. So now who can give me the closed loop characteristic equation is equal to what? The problem that we need to solve. We find D. This one is D, huh? This one is D of S. So simply now T of S, which equal Y over R, which equal N over D is equal. Now I'm having the D, S square, plus 2S, plus 112.75. Here, what I should put?
6.
Are you sure?
Yes. Y steady state, صح?
Why
No,
still
no.
state?
No.
Just a minute. I told you that here for that problem or for this problem, if the input is unit step and I'm having 6, simply I need to multiply 6 by the omega n square to make the DC value equal to what? To 6. But because here I'm assuming that the input is what? Here, my assumption is what? The input is what?
6.
6. So simply the DC gain must equal to what? 1. Yeah, because the AC state is equal to 1. And this the response here is for a step response for R of T is equal 6 U of T. Yeah. In this case, the DC gain is equal to 1. So here I should put 12.75. Yeah. Now the DC gain here is equal to what?
دكتور عيدها لو سمحت.
Okay. Now, you know that the DC gain is shaping the output, correct?
Yes.
The DC gain will shape the output. Now here I'm assuming that the input is 6, yeah?
Yes.
Not unit step. If this one is unit step, okay, I will solve it in two. I will solve it in two, let's say in 2 ways. The first one, I'm assuming that the input is not step, the input is 6 U of T. Good. If the input is 6 U of T, then simply this means that this system has a DC gain equal to 1. Why DC gain equal to 1? Because the error is equal to 0. Is the state due to the step input is equal to 0. Yeah?
Yes.
If this correct, then the DC gain is equal to 1. Yes?
Yes.
Good. So now the DC gain is equal to what? The DC gain is the value at S equal to what? 0. Yeah? This is actually what we call it the DC gain. So here I would say K DC. So now let's assume this one is unknown, and for that I will use alpha. So alpha over S square plus 2S plus 12.75. If I evaluate at S equal to 0, what I should get? 1, correct? If the DC gain is equal to 1, according to my assumption, yeah?
Yeah.
So in this case, alpha is equal to what? Yeah?
Yes.
This under the assumption that the input is 6 U of T. Yeah. Now, what about if I change this assumption? Of course, this one will change the error. Huh? So what about if no? The response, the above response is for a unit step. In this case, R of t is equal to what?
1.
1, which is U of t. Yeah. So simply here, E steady state due to step input, unit step input, will equal to what?
-5.
Yeah, it will equal R steady state minus Y steady state, which equal 1 minus 6 equal to -5. So now the type number is equal to what? Equal to what? If I'm having error, the type number is 0, correct? If I'm having error due to unit step input, then the type number is equal to 0, yeah?
Yes.
Do you see? I'm only changing the assumption of the input. I changed the problem, correct? Yeah. The same thing here. Now, the DC gain here is equal to what? In this case, equal to what?
6.
Equal to what? 6. Yeah. Why? Because I'm injecting 1. What I'm getting? I'm getting 6. So the DC gain equal to 6. So can you now give me alpha equal to what? So now alpha equal to what?
76.2.
Which is 6 multiplied by 12.75, which is 76.2 according to Raha.
Oh.
Good. So now let's discuss this thing. Now, this is the same problem, What only I'm changing? I'm changing the assumption of the input, correct? This change a lot of things in the problem, how to solve, yes. So simply in the same thing in the exam, maybe you are receiving, let's say, the same problem, but simply I'm changing something. And this does not mean that the sequence will be the same. No, it's not. So here everything is changing. The type number is changing, the error is changing, yeah, and the transfer function in the end of the day will be changed. Understood? Understood?
Yes.
Okay. Do you have any question regarding chapter 5 before finishing it? And start with chapter 6, which is the stability of a linear feedback control system. No question? Anything? Okay. Let's see. Okay. I am on hold. Can you hear me?
Yes.
دكتور yes.
دكتور.
Yes, doctor.
What's the problem? Okay, anyway. So, any question? No, no question. Okay. Okay. I'm not sure what happened, but whatever. Okay. So you still can see my screen?
لا دكتور.
لا.
Now?
هسه.
هيك لا.
Okay. So if there's no question, let's start with a new chapter, which is actually chapter 6. And this one will be discussing the stability of linear feedback control system. So here we are discussing old and new topic, which is the stability of feedback control system of a linear control system. And why this one is old and new? Because in the end of the day, whatever you are designing, the first requirement is the stability. The system must be stable. If the system is not stable, then nothing you can do. There's no response at all. The response will diverge to infinity. So you cannot say anything about the rise time, the settling time, the percent overshoot, the steady state error, because it's undefined. It will escape to the infinity. Why? Because the system is unstable. So the first thing we should check is the stability of the system. So how we can check the stability of the system? So here I will write that stability of a closed loop control system is central to the control system design. The most important issue, actually. Simply, if your system is unstable, nothing you can do. If your system is unstable, nothing you can say about the rise time, the settling time. It's undefined, actually. So the first thing you should ensure the stability of the system. If the system is unstable, we should design the controller in order to maintain the stability, or to put the system in the stability. So what's the meaning of the stability? In general, as a broad sense of the stability, if I'm having a system and this system has a bounded input and the response or the output of the system was bounded, so bounded output, now this system is called bounded input, bounded output stable system. Yeah. So in general, the stability has no relation with the input. It's only related to what? To the system itself. And for that, let's assume I'm having the following example. Let's assume that here I'm having, let's say, a pendulum. You know the pendulum? Let's assume here I'm having a pivot, and here I'm having a rod. Here I'm having a rod, and in this rod here I'm having a mass. Let's assume a mass here, a certain mass. And simply this joint, I can move it in a clockwise or counterclockwise direction. Now let's discuss the first scenario. Let's assume that the system is starting from the following point. And now it's free to oscillate, what will happen to this system? What will happen to the system? Now you know that the ball will go until certain height, and if there's a friction, you know that the new height will be less than the first height, correct? Let's assume here we have friction. Of course, we have friction. Yes, we have the drag force from the air. We have friction. So what will happen here? So simply, if I visualize, let's say the motion of the ball, it will be something like this. Correct? Until it is settled down at the zero position. Correct? Yes. It will oscillate. The potential energy will be converted to the kinetic energy. Then the kinetic energy will be converted to the potential energy. But because I'm having friction and losses, this means that certain energy will be lost in the way. So swing, oscillate until I'm reaching to what? To the equilibrium point or the origin, let's say. So this system is called what? Stable system. Now, what about if I'm having the following scenario here too, that no friction? I'm assuming that
undamped,
which means that
oscillate forever.
Oscillate forever. Yeah, thank you. So simply this means that this ball, if you start from initial position, let's say, it will swing here, then return back here. Yeah. So if I visualize it, it will be something like this. Yeah. It will oscillate forever with fixed amplitude and fixed frequency. Yes. And this one is called what? Critically stable or marginally stable. Yeah. Later on, I will discuss with you why we call it critical stable or marginally stable. So simply here the response will oscillate forever with fixed amplitude, fixed frequency. Correct? So what about the unstable system? Now let's assume someone is interested in balancing the ball in the upside position. So simply let's assume now someone is interested to do this one. And to maintain the ball here, let's say. Now, what will happen here if any small disturbance happened or whatever? If this one is not balanced 100% due to the asymmetry, whatever. And if I'm starting the ball or the pendulum, let's say, this one's called inverted pendulum. If I'm starting the inverted pendulum at this position, what will happen?
He will fall in the right side.
Yeah, so simply the ball will go here, oscillate and go here, yeah? Yes? But simply this is my target. This is my point I'm interested in. The stability is here. I need my system to be stable at this point. So this system is called what? Unstable. Why unstable? Because any disturbance, any variation here, it will make the state or the ball go away from this point, correct? Yes, it will go away from this point. So this one is unstable. Or if we need another example, let's assume we have, so this one is called unstable system. Let's assume now we have the following example. This is a ball. Let's assume we have the following case. And here I'm having a ball. Yeah. Now the same thing. If I'm having friction, if there is a friction, and I'm starting at this point, what will happen? The ball will swing, return back, swing and return back, swing and return back until it's what? It settles down at this point, correct? So it will go something like this. Yes. So the same thing. This one is what? Is stable. Now, if there's no friction, and I'm having the same system, and starting from certain point here, what will happen? It will swing forever with fixed amplitude and fixed frequency. So if I visualize it here, it will be this, you know. The same thing, this one is called what? Critical stable. Yeah. Now, what about if I'm having the, this is called the critical stable. And here, what about if I'm flipping this like this? And now my ball here. Now, if any disturbance happened to this ball, a wind or small variation, what will happen to the ball? Yeah. In this case, what will happen to the ball? If I push this ball slightly, what will happen?
It will fall.
Yeah, it will fall. So simply, if I plot it to be something like this, correct? Yeah.
Yes.
So this system is unstable. Yeah. So the meaning of the instability that the system exceed the boundary, exceed the boundary or the constraint of the system or the limit of the system. Mathematically, this means that the state go to where? To infinity. Mathematically, the state go to infinity. Yeah. So if mathematically the state go to the infinity, this means that the exponent here, the exponent here is positive or negative?
Positive.
Positive.
Positive, yeah. You know that if I'm having, for example, a second order system, then y of t will be certain, let's say beta, plus exponential minus sigma t, yeah, sine omega d t plus certain angular phi, let's say. Yeah? Now, if the system is unstable, this means that sigma must be what? Sigma must be what? If the system is unstable, sigma must be what? Negative. Negative. So simply this means that the real part of the root is positive or negative. And remember, the roots here in general, if I'm writing a second order system root, it will equal minus sigma plus minus j omega d. So this means that if the system is unstable, then the real part of the root will be what?
Positive.
Positive. Yes. And if the system is stable, then simply the dynamic must go to where? To the zero, and I will end up with what? With y steady state, yeah? This means that if the system is stable, then the real part of the root must be what?
Negative.
Negative. Why? Because I need my exponential, the exponent in the exponential to be what? Negative here, correct? Yes? Yes?
Yes.
Yes.
Good. Now, what about for the critical stability? Here, do you see any damping? is the oscillation will reduce, let's say, or the oscillation will maintain in the same rhythm, the same frequency, and the same amplitude.
Will remain the same.
So simply here, the real part will be equal to what?
0.
Zero. So this will be a complex, pure imaginary, yeah?
Yes.
Yes. In this case, this one will be pure imaginary. So this is very interesting because from the roots, the closed loop characteristic equation roots, I can judge about if the system is stable or unstable or critically stable. Yes? Yes?
Yes.
Good. So simply, this is very interesting. Here I will write that the stability of the system actually is directly connected to the location of the roots of the characteristic equation. So here I will say that the stability of the system is directly connected or related to the location of the roots of the characteristic equation. Yes? Yeah? The meaning of the location is what? The meaning of the location is what? If this is the
Left
complex,
or right, the imaginary axis.
yes, if this one is the complex as plane, and this is the real, and this is the imaginary. So simply for stability, all the roots of the characteristic equation must locate where?
Left of the
Yeah, must
imaginary axis.
be located to the left of the j omega x. Yeah, of the j omega x. Which means that all the roots of the characteristic equation have or having negative real part, correct?
Yes.
Real part. So someone will say this is actually the region of stability, yeah? If all the roots of the characteristic equation are located here, then the system is what? Then the system is stable, huh? Yes?
Yes.
Good. Now, what about the instability? What about the instability?
One of the root has to be right of the
At
imaginary
least
axis.
one. At least once. Yes?
Yes, at
So-
least one.
Yeah, at least one root of the characteristic equation is located to the right. Yeah? To the right of the j omega x. Correct? Which means that at least one root has a positive real part. Yeah? Yes?
Yes.
Why at least one? Because you know that if one mode is unstable, all the system will be unstable, correct? One root has a positive real part, correct? Yeah. Now, what about the critical stable? So this one here. This one here is what? For unstable system. Now, you know that here I'm having what, let's say two regions. One is stable and one is unstable. In between, I'm having the j omega x, the boundary, correct? What about the boundary here? The j omega x. What about the boundary? The j.
If one root locate on the imaginary, it's critical.
I will not say one. I will say simple root. Why? If I'm having complex, you know the complex impossible to be one root. The complex must be paired. Yeah.
Yes.
So
Plus
I will say
sometimes.
that simple root. I will say 3. If a simple root located on the j omega x and all the other roots were
Left.
yes, must be on the left. If one on the right, I don't care. If one on the right, the system is what will be unstable. Huh? If a simple root located on the j omega x and all the other roots are in the left half plane, then in this case the system is called what? Critical stable. The system is critically stable, or sometimes we call it marginal stable. Yeah, or sometimes we call it marginal stable. So this one for stability, stable system. And this one is for unstable system. And those are necessary and sufficient condition for stability. Now I will put line under symbol. The meaning of the symbol is 1. If the root, it can be 1 at the origin, this is what? A simple root. At s equal to 0. This is called simple root. Now what about if I'm having a pure imaginary? So one here and one here, let's say j omega and minus j omega. This is also called a simple root. This is also called a simple root. Yeah. Now why this one we call it critical stable? This one we call stable, this one is unstable, but this one we call it critical stable. Why? Do you know why? Why if I'm having simple
ممكن لانه بضل oscillate forever بس بضل محصور بين قيمتين، مثلا اذا كان ساين ولا دي سي ولا، بس بضل محصور بالنهايه مثلا بين 1 وماينس 1 ممكن، او مثلا بين قيمه معينه، بس انه بضل forever يستمر.
Can this system be unstable in any sense?
قصدك الماجنتيود goes to infinity؟
Are you sure?
Because the average are
Average are what? Are 0?
have a constant value.
Okay, let's discuss the following simple example for the critical stability. So here I will put 3. Let's assume I'm having y over r is equal 1 over s plus 1. This one, is it stable, critical stable, or unstable?
critical stable.
Yeah, why? Because r simply d, or the characteristic equation, which d equal to 0. D equal to 0, which is my characteristic equation, state that s plus 1 equal to 0. So the root is s equal to 0, and the root is s equal to minus 1. Yeah. So I'm having a simple root where at the j omega x, correct? Simple root, and all the other roots located where in the left half plane. So this is the condition of what? Of the critical stability, correct? Yeah. This is the system is what? Is critically stable. Now, why this one is called critically stable? Now, let's see. Let's assume we know that stability is not related to the input, correct? It's only characterization of the system itself. But for this system, if I'm injecting R equal 1 over S unit step, what will happen? What will happen here? Can anyone give me y equal to what now? It will equal 1 over S squared, S plus 1. If I do the partial fraction expansion, this will equal to what? K1, certain constant over S. Can you continue with me? Plus what?
K2 over S square.
Yeah, thank you. Oh, plus what?
K3 over S plus 1.
Can you give me now y of t is equal to what? The Laplace inverse of the first term is K1. The Laplace inverse for the second term is equal to what?
T K2.
Thank you. Plus t K2 plus the Laplace inverse for the third term equal to what?
K3 equal minus 1.
Now this system is stable now or unstable?
Unstable.
Yeah, because if I need to find y of infinity, it's equal to what? To infinity. Yes? Yeah? Yes?
Yes.
Due to what? Due to the t. Yeah? So simply this states that the critically stable system produce a bounded input to the produce a bounded output to the bounded input, except for an input which is the frequency match the frequency of the simple root. Now the frequency of the simple root, this one, is equal to what? 0, correct? The frequency, this is the j omega x, and this one located at the origin. So the frequency here is equal to what?
0.
And this input, step input, unit step, the frequency of the unit step is what? DC. 0. So now my input frequency matched the simple root frequency, then the system becomes critically stable. That's why this is called critically stable. And I think this one you already know from the high school. Do you remember when we all the time in the physics we say that if there's a soldiers trying to cross, let's say a bridge. I'm not Picasso, but I will try my best. If there's a soldier here, and you know if the soldier is moving, they will move in uniform motion, correct?
عشان ما يتدمر الجسم.
Except on the bridge. On the bridge, each one of them will move in his own, let's say, motion. Why? Do you know why?
عشان ما يتسبب قوة تدمر الجسر.
Yes, because they're afraid. There is a chance that their frequency will match a simple root on the j omega x, and this will do a collapse for the bridge. Yes? We call the resonance in the circuit actually this one, huh? Yes?
Yes.
So the same thing if I'm having what? A complex roots, a simple root at the j omega x, and for that also I will recall 3. And I will assume that I'm having y over r, which will equal, let's say, 1 over s plus 5, multiplied by s plus, let's say, 16 square here. Now, this system stable, critical stable, or unstable, and why?
Critical stable.
Critical stable. Let's see. Now the roots s equal to -5. This is in the left half plane. This one in the left half plane. And I will end up with s equal plus minus j4. And this actually what? Simple root where? Simple root at the j omega. Correct? If I'm plotting the j omega x, this is the real, this is the imaginary. I will get 1 here at 4 and 1 here at -4, correct? This is still simple. Yeah. Now, this one, if I inject it with input R equal sinusoidal input, yeah, sinusoidal input, with the frequency equal the frequency of the symbol root. The frequency of the symbol root here equal to what?
4.
4.
4. So simply this means that I will end up in the end of the day y is equal 1 over let's say s plus, here I'm having s square plus 16 all square, correct? And here I'm having certain let's say a constant I don't care about, yeah, correct? Because I'm injecting what? A sinusoidal with the same frequency, so I will have this one repeated, correct? Now if I do the partial fraction expansion, this will equal to what? Certain constant, let's say k1 over s plus 5 plus another constant k2 over s square plus 16 plus another constant k3 over what? S square plus 16 all square, correct? Now y of t equal to what here? The first one here, this one, y of t of this one is what?
K1
K1
by e to the power of -5.
Yeah, so the first one is exponential stable system. This one is k1 exponential minus 5t plus, what about the second one here? Now this one will be the sign, I think, correct? Yeah, this one will be, let's
K2.
say not k2, it will be something, because here I
K2
need
over
constant.
4.
Yeah, k2 over 4. If you need to calculate it, will be k2 over 4, and this will be what? Sine 40
4.
plus. What about this one?
مش نشتق الساين اوفر نفسها، بس مشتقة نفس اللي قبل. نشتق
4, but here you have t. Yes.
yes.
Sine 4t. Now the same thing here. Y of infinity equal to what?
Infinity.
Infinity. So the same thing, huh? Now the critical stable is actually produce a bounded output for all the inputs except an input where its frequency match the symbol root frequency, correct? That's why we call this one what? Critical stable system. Before finishing this lecture, let's take the following simple example to highlight the meaning, certain meaning, something, something in the heart of Jacob, let's say. Let's assume here I'm having 6 over s minus 4, and here I'm having a negative feedback. This is R, this is Y. The closed loop system, stable, unstable, or critical stable? Is stable or unstable or marginal stable or critical stable? Answer this.
stable.
Why stable?
لأنه في عنا positive feedback فبصير ال characteristic equation s minus 4 minus 6.
Actually, this will be unstable. Because if I'm taking the closed loop system, it will be 6 over s minus 10, correct? Yeah?
Yes.
And the root s equal to 10, which is located in the right half plane, and the system will be what? Unstable. But let's assume here I'm having a negative feedback. Now, the system is stable, unstable, or critical stable?
stable.
Why stable?
لأنه عندي 6 over S plus 2.
Now see, the open loop system is stable or unstable?
Unstable.
The open loop system is unstable, correct?
Yes.
But the closed loop system is what?
Stable.
So, and this is the beauty of the closed loop system. I can modify the stability. Even if the system is unstable, using a simple feedback, the system become what? Stable, correct? Using what? Using only a simple feedback. So even if the system, if the open loop is unstable, this is not the end of the road. Simply, I can design a controller, I can design a configuration such that I can make the system is stable. If the system is stable, later on, I can now discuss the requirement or the desired performance that I need to achieve. And here I will stop.
دكتور.
يب.
مش لازم تكون 1 زائد 6 على S ناقص 4.
1 زائد yeah, and I think I did that here. Correct?
Yes, this is correct.
This one's correct. And maybe here I'm missing. It's 1 plus, yeah, thank you. But this answer is correct, actually. I'm adding, huh? That was the one for the positive feedback. Yeah. Good. Do you have any question?
دكتور كويزنا الأحد 8:30 صح؟
Yes. You will log in to the e-learning at 8:30. The quiz will be opened only for 10 minutes. You have 10 minutes. It will never extend it. After 10 minutes, you will enter to the lecture. Understood?
تمام دكتور شابتر 5 صح؟
Yeah. The weight will be 5 points, inshallah.
Okay, thank you.
Okay. Now, do you have any question?